Welcome back, ladies and gentlemen. Today we're going to tackle sections 12.7, the volume of similar solids. Up on this screen, you'll see our exit question for the day. To get started, I'm going to show you your one and only theorem for the day, and technically we've already talked about it before in section 11.3 when we talked about the area of similar shapes. And the same pattern follows that we discussed in that video, which is that if you have a scale factor relating two shapes in terms of their lengths, if you want to know how their areas relate, you just simply square that scale factor, so a squared over b squared. And today we're going to talk, if you want to talk about their ratio of volumes, then you cube the original ratio of a cubed over b cubed. So to practice, I just want to see if you can pause the video and fill in this chart, and I'll talk about how to do that in just a moment. Alright, to do this, let's start from the top row and then go middle row and then bottom row. To start on the top row, we'll go with this. This is the original scale factor. So this one's pretty easy. All you have to do is square it and then cube it to go from left to right. So squaring it would get 9 over 25 and cubing it would get 27 over 125. The next row is a little bit more challenging because we start all the way over in the volume category, which means it must have taken the original scale factor and cubed it. So to go back to that, we would have to take a cube root, okay? Cube root of 343, which is 7, and the cube root of 64, which is 4. And then to get the area one, we're going to square this little guy to be 49 over 16. Now notice in this, I was not able to go from volume to area to length. I had to go from volume way back to the original and then back forward again to the area proportion. Similarly, in this last one here, we're going to have to work around, we're basically going to have to go back to the scale factor and then jump ahead to the volume ratio. So first things to notice is that this is not simplified and neither of those are perfect cubes. So let's try simplifying it and seeing if we can get perfect cubes. And if you simply divide by 2, you get 81 over 100, both of which are, perfect squares we were looking for. Both of these are perfect squares, so then we can take the square root of them, get 9 over 10, and then we can take our original scale factor and cube it to get up to 729, which is 9 cubed over 1,000, which is 10 cubed. The next thing I have for you is simply a list of the perfect cubes, and we're all very good at recognizing and using and taking the square root of perfect squares, but we haven't done very much with cubes so far in math, so here are the first 10 perfect cubes. It's worth writing down and it's worth memorizing a few of them just so that you recognize, hey, 512 is actually a perfect cube. And it helps you out in a few cases so that you're able to recognize when a perfect cube is being used or maybe a multiple of a perfect cube is being used. The second little helpful hint that I have is if you have any platonic solid or a sphere, or if you have two of any of those, they are similar to each other because with the example of the platonic solids, all the faces are regular polygons and all regular polygons are similar, so it would make sense that all solids that are made of regular polygons, the same type of regular polygon, are similar to each other. And it should be pretty obvious that all spheres are similar to all spheres. So you can feel free to use those facts as they come up. Next is our first example. Take a moment to write down the drawing, all the labels and the directions for it. Alright, our goal here is to find the surface area and volume of both solids 1 and solid 2. You'll notice that in the drawing that we know an awful lot about solid 1 in terms of its dimensions, but we don't know a lot about solid number 2. We are told that they're similar, so instead of working through this very painfully and converting all these lengths, you notice that they do share a length being labeled of 4 and 10, so you could technically convert all of these dimensions, so you could, through that proportion factor, or through that scale factor, to figure out what is the height of the top of the cone here and what is the radius here. I suggest not doing that because you're basically going to double the amount of work that you have to do. So let us instead figure out everything that we can about solid number 1. If we can figure out the surface area of solid 1 and the volume of solid 1, knowing that they're similar, we will be able to figure out the area proportion and the volume proportion so that we can just simply scale up what we got for solid 1 into solid 2 without having to add together all the different pieces of all the different shapes to figure out the surface area and volume of solid number 2 by using all the dimensions that we would also have to convert. So given that this is a composite solid, this is going to save us a lot of time. So why don't you see if you can come up with a game plan to figure out the surface area and the volume for solid number 1. And once we have those bits of information, we'll use the scale factor to convert to the surface area and volume of solid number 3. Or solid number 2, I'm sorry. Alright, here's my game plan. My game plan is to find the surface area and the volume of solid number 1, and in order to find the volume of solid 1, we have to add together a cone and a cylinder. So I simply have the volume of a cone plus the volume of a cylinder. The surface area is a little bit more complicated. I have the label of a cylinder, or the lateral surface area of a cylinder. I have the lateral surface area of a cone, and I have the circular base to deal with. So I have the lateral surface area of a cone, the label of a cylinder, and the base of a cylinder as well. So now we've got a whole lot of ideas. You need to kind of figure out what those formulas are. So see if you can page through your notes and figure out all the formulas that go along with all of those shapes that I just mentioned. We have talked about each one. If you found all of those successfully, the lateral surface area of a cone is pi r times the slant length. The label of a cylinder is 2 pi r h, capital H meaning the height of the cylinder, and pi r squared for the circle. For the cone volume, it's 1/3 pi r squared h, and for the cylinder, it's pi r squared h. Again, capital H referring to, in this case, the height of the cone, and in this case, the height of the cylinder. So a little bit tricky on that. So let's see what we know. It looks like we are missing a slant length, so we're going to have to come back to that later, but we do have a height for each the cone and the cylinder and a radius. So we can do the volume right now, and if you do that, you get 62.83 cubic feet. To find the slant length, we're going to have to take a cross section of that cone and perform a little Pythagorean theorem on that. So 2 squared plus 3 squared equals L squared, which gives us a value of L of 3.606. That's an irrational number that I rounded, just FYI. But let's keep it in there and just go with it. Plug all the numbers in and get your surface area for solid number 1, just like so. The next step, to find all the information for solid 2, we need to use the scale factor for areas and volumes to convert from our surface area of solid 1 to the surface area of solid number 2. So let's take a look at the scale factor that we need, and you'll notice that there's only one corresponding length or area or volume that is labeled, and that is the 4 foot to 10 foot. So I'm going to write a ratio of small to big, which would be 4/10, and that corresponds to our lengths. That's not simplified, so I'm going to go 2/5, and then I need the appropriate scale factors for area and volume. So I'm going to take that and square it, and I'm going to take that and cube it to get 4/25 and 8/125. Now, we've done all that work, and technically you could have done all that work before this lesson. So now is the actual part of the lesson where you have to apply the new idea, and that is to write two proportion equations, one that'll help you go from the surface area of solid 1 to the surface area of solid 2. So you're going to use that ratio of areas and the area that you know to write a proportion equation. And you also have to write a proportion equation that will do the same, but this time with volumes. So see if you can pause the video and write those two proportion equations that will allow you to solve for the volume of solid 1 and, the volume of solid 2 and the surface area of solid 2. If you write those proportion equations correctly, you get a little something like this. And I wrote it from small to big, small to big. So our ratio of areas was 4/25, and our area of solid number 1 was 84.49, and then we're going to solve for that. And then likewise, we got small to big, and simply cross multiply and solve. And if you do that, you get the surface area being 528.06 square feet, and the volume being 981.72 feet. Just a reminder to put on appropriate labels whenever you get an answer like that, or generic square units or generic cubic units if it's not mentioned. Up on the screen, there's our assignment next time I see you, and I think that's the end of the book, so congratulations. Have a great day.